Welcome to a deep dive into how we truly understand science itself. Not just, what it discovers, but how it actually works, what it can really tell us, and maybe most importantly, what makes something science. We're diving into the pretty fascinating world of the philosophy of science. And think about it, science shapes our lives in huge ways. Your phone, the medicine we trust, none of that exists without scientific theory, scientific methods. Science has this kind of unparalleled prestige. We often trust scientists more than journalists or lawyers, maybe even politicians. We rely on scientific evidence for really crucial decisions, justice, health, safety. But okay, this raises some really fundamental questions, doesn't it? What is science, actually? What kind of knowledge are we getting from it? And how do we know it's true? These aren't questions you can just answer with an experiment. This is where philosophy of science steps in. It explores these big questions through, analysis, argument, debate.
Right. And what's fascinating here, I think, is that while other fields might look at the history of science or the psychology of scientists or, the sociology, philosophy of science pushes us to reflect on its fundamental nature. It's asking not just what science tells us, but how it tells us, and really, why should we believe it?
So, okay, our mission for this deep dive, let's try to unpack the core philosophical debates about science, from its very foundations all the way to how we interpret its biggest claims. We'll explore the different views on what makes something scientific and, can we really trust what our best theories say about the world, both the bits we can see and the bits we can't?
And that raises a really important point. If science is so crucial, how exactly do we define it? How do we tell genuine scientific claims apart from things that just sort of adopt the appearance of science?
Yeah, let's start there. Philosophers call it the demarcation problem, basically drawing a line between science and non-science, especially things like pseudoscience. You think about debates over, say, creationism in schools or claims about IQ testing, parapsychology, astrology. How do we decide if something's really science?
Historically, the answer often comes back to the scientific method. There's this widespread belief that if something's scientific, it's because it follows a specific method, right? A set procedure.
Okay, let's dig into that. Maybe a quick historical journey. The scientific revolution, that was a huge break from the older Aristotelian ways of thinking. People were actively looking for a new tool for knowledge.
Yeah, the Aristotelian view, which held sway for centuries, put the earth at the center. The heavens were perfect, unchanging, earthly stuff, imperfect, always changing. And knowledge back then was mainly about deduction from first principles, sort of reasoning about the essence of things, not so much about direct sensory experience, which obviously leads to the question.
How do you learn about the natural world if you aren't really looking at it?
Exactly.
So here's where it gets really interesting. Francis Bacon, 1620, Novum Organum. New tool. He saw science as this collaborative thing, a systematic process. Gather information, produce useful and sure beliefs. He's the one often linked with knowledge is power, right? Really emphasizing the practical side.
Right. And Bacon's method was all about avoiding what he called the idols of the mind. These are basically biases that mess up our understanding. Idols of the tribe, like our human tendency to see patterns where there aren't any. Idols of the cave, our own personal prejudices. Idols of the marketplace, getting tripped up by language. And idols of the theater, mistaken philosophical systems, like Aristotle's, he thought. So he pushed for observation free from these preconceptions, using natural and experimental history. And he had that famous phrase about torturing nature for her secrets through experiments, basically making things happen that wouldn't normally happen.
Okay, so the core of Bacon's method, two pillars, unprejudiced observation and induction. Induction is, it's reasoning from specific past observations to broader general conclusions or future predictions. If every piece of metal we've ever heated has expanded, we induce that all metals expand when heated. Seems straightforward.
But here's the rub. David Hume comes along and asks a really powerful question. How do we justify induction? Hume made this key distinction. Relations of ideas, things true by definition, like math, bachelors are unmarried, negating it is a contradiction. Then there are matters of fact, truths about the world. Snow is white. These are based on experience. And crucially, Hume says you can always imagine the opposite of a matter of fact without any logical contradiction. You can imagine snow being black.
So what's the big insight from Hume here? What stands out?
He argued we never actually experience a necessary connection between cause and effect. We just see a constant conjunction. One thing follows another, always. We see one pool ball hit another, the second one moves, every time. But we don't see the making happen, we just see the sequence. So connecting this back, Hume concluded that our belief that the future will be like the past which is the absolute bedrock of induction, is itself justified only by past experience. Which is circular reasoning. You're using induction to justify induction. He famously said our inductive habits are based on animal instinct and habit, not reason, which casts serious doubt on the rational foundation of, well, pretty much all our empirical knowledge, including science.
Wow, that's profound skepticism, isn't it?
Yeah.
If Hume's right, then even simple beliefs like bread is nourishing aren't rationally justified, just habit.
Exactly. It's a radical conclusion, and understandably, many philosophers push back. One response is just to say, look, induction is rational by definition. That's just what we mean by rational in everyday life when we're talking about the world. But just calling it rational doesn't really prove it leads to truth, does it? Others try to sneak in a premise, like a principle of uniformity of nature, to make inductive arguments deductively sound. But then you just have to ask, how do you justify that principle? You've just pushed the problem back a step.
And it feels even more complicated in practice, right? Our inductions aren't usually that simple. We don't just assume our next breath will come because the previous ones did. We know humans eventually die. We use all sorts of background knowledge, which makes Bacon's idea of purely presuppositionless observation seem, well, not just impossible, but probably not even helpful in modern science, which relies so heavily on existing theories. Okay, so if induction is problematic, how does science move forward? How does it build knowledge? This is where Karl Popper comes in with a really different, almost radical alternative. Falsificationism, his big idea. Science shouldn't try to confirm theories. It should try to falsify them, break them.
Yeah, the key insight for Popper is this logical asymmetry. Think about swans. No matter how many white swans you see, you can't logically prove the statement all swans are white. There might always be a non-white one you haven't seen, but you only need to see one black swan or any non-white swan to definitively disprove all swans are white. So Popper argued, the inference from that one falsifying case to the theory being false is purely deductive logic. It completely sidesteps Hume's problem of induction.
And Popper was apparently really impressed by theories that made risky predictions, right? Novel ones. Like Einstein's theory predicting starlight would bend around the sun during an eclipse. That was a bold, risky prediction. It could easily have been wrong. Or Mendeleev's periodic table predicting elements that hadn't even been discovered yet. For Popper, real science sticks its neck out. It makes precise, surprising predictions. And critically, scientists have to be willing to ditch their theories if those predictions fail.
Right. And this leads to his criticism of what he saw as pseudosciences, like Marxism or Freudian psychoanalysis. He argued they were often too vague to be properly falsified. Or they had these built-in ways to explain away any criticism. Like, if you disagreed with Marx's theory, well, that could just be dismissed as your class interest talking. This kind of foreclosing of criticism, as Popper saw it, was fundamentally unscientific.
So what's the upshot then, according to Popper? What is scientific knowledge?
For Popper, it's always provisional. It's always just a conjecture that has not yet been refuted. This is known as fallibilism, the idea that any of our knowledge claims could, in principle, be wrong and are open to correction. It's sort of an anti-authoritarian view, really, which tied into his broader political philosophy, too.
Okay, that makes sense. He also drew this line between how you come up with an idea and how you test it.
Exactly. The context of discovery versus the context of justification. How you dream up a theory could be a dream, a hunch, metaphysical beliefs, whatever that's irrelevant to its scientific status for Popper. What matters is the justification. Can it be rigorously tested? Can it potentially be falsified? Philosophy's job, he thought, was to focus on that justification part.
It sounds neat, very logical, but it's not that simple in practice, is it? There are challenges, like the Duhem problem, sometimes called the Duhem-Quine thesis. It points out that you never test a hypothesis all by itself. You're always testing it along with a whole bunch of background assumptions, auxiliary hypotheses.
Right, assumptions about your instruments working correctly, about the initial conditions, about other background theories being right.
So if your prediction fails, you don't actually know for sure if the main hypothesis is wrong, or if one of those dozens of auxiliary assumptions is the culprit.
Duhem himself said scientists use good sense to figure it out, but that's not exactly a rigorous logical rule, is it?
And what about things in science that just seem unfalsifiable?
Yeah, that's another tricky area. Probabilistic statements, for instance, like radioactive decay. If you have an atom that's supposed to decay within a certain time based on probability, but it doesn't, does that falsify the theory? Not really, it was just improbable. Or existential statements, black holes exist. If we fail to find one, does that prove they don't? No, we might just not have looked in the right place or had the right tools yet. And think about fundamental principles, like the conservation of energy. When scientists observe something that looks like energy isn't conserved, they don't usually throw out the principle.
They look for a new kind of energy, right? Like with neutrinos.
Precisely. They postulate something near to save the principle. So is the principle itself truly falsifiable in Popper's sense? It's debatable.
And then there's that other issue we touched on, theory-ladenness of observation. If the theories we already hold actually influence what we observe or how we interpret it, like a trained doctor sees things in an X-ray that I just wouldn't see, or a physicist interpreting particle tracks in a detector.
Or the classic example, does the sun rise or does the horizon fall because the Earth is turning? What you see can depend on whether you hold a Ptolemaic or Copernican view.
If observation itself isn't neutral, can it really be the objective judge between theories that Popper wanted it to be? This whole idea that maybe observation isn't neutral, that maybe science isn't just steady progress, leads us straight to Thomas Kuhn. His book, The Structure of Scientific Revolutions, back in 1962, it just completely shook things up. Kuhn basically said, forget this idea of science as this continuous cumulative buildup of knowledge. He argues science operates within paradigms.
Right, and Kuhn's concept of a paradigm, or later he called it a disciplinary matrix, is really rich. It's not just a theory. It's a whole way of doing science shared by a community. It includes shared beliefs, fundamental laws, yes, but also shared values like what counts as a good explanation. It includes standard techniques, mathematical tools, key experiments or achievements that serve as models, what he called exemplars. Think of Newtonian physics. It was a whole package. Laws of motion, gravity, but also a sort of clockwork view of the universe, specific math techniques, Newton's Principia as the gold standard.
And during what Kuhn called normal science, scientists aren't trying to overthrow the paradigm, right? They're working within it, solving puzzles, extending its reach, refining measurements, dealing with little anomalies.
Exactly. And Kuhn argued that scientists are often, and maybe even should be, quite committed to their paradigm. You don't just throw out a hugely successful framework like Newtonian mechanics because of one or two weird results or anomalies. It's often rational to stick with it, try to make the anomaly fit, assume there's an experimental error or a refinement needed. There's a huge investment there.
But sometimes those anomalies pile up.
Yes. Sometimes anomalies resist all attempts to solve them within the existing paradigm. They accumulate, maybe become more central. This can lead to a crisis phase where confidence in the paradigm starts to wobble. And eventually, this might trigger a scientific revolution, a radical shift, a wholesale abandonment of the old paradigm for a new competing one, like the shift from Ptolemy to Copernicus or Newton to Einstein.
And Kuhn suggests these shifts aren't purely driven by logic and evidence.
Well, that's the controversial part. He looked closely at historical cases, like the Copernican revolution. The old Ptolemaic system, Earth-centered, it worked pretty well for predicting planetary positions for centuries. Copernicus's sun-centered theory initially was not clearly more accurate. In some ways, it was less accurate without adding complex adjustments, and it clashed massively with common sense we don't feel the Earth moving. It clashed with the accepted Aristotelian physics of the time. And even observations, like the fact that Venus didn't seem to change size dramatically as it would if it orbited the sun closer to us sometimes, though later Galileo saw phases with his telescope.
So why did people adopt it then?
Kuhn points out different people were persuaded by different things. Some liked its mathematical harmony or simplicity. Some maybe had Neoplatonic philosophical leanings favoring the sun. It suggests that factors beyond just empirical evidence and logic, maybe aesthetic preferences, metaphysical beliefs, even social factors play a role in these big revolutionary shifts.
Okay, and this leads to his really challenging idea of incommensurability.
Yes, incommensurability. The idea that competing paradigms can't be perfectly compared or translated. They might use the same words like mass or planet, but mean slightly different things. Their standards of evidence might differ. What counts as a problem worth solving might differ. Even what counts as observable might differ.
So you can't just line them up and say, this one fits the facts better.
It's not that simple, Kuhn argues. It's more like trying to translate between two very different languages or cultures. There's no neutral language to use for a perfect comparison. This then raises deep questions about scientific progress. If paradigms are incommensurable, can we really say science is getting closer to the truth about an objective reality? Some took Kuhn's ideas even further towards what's called social constructivism, the idea that scientific facts are essentially created or negotiated within scientific communities, not discovered out there in the world. Maybe electrons are constructed by physicists in labs.
Wow. Okay, so these ideas, the problems with induction, the theory-ladenness of observation, Kuhn's paradigms and incommensurability, they all feed into this really central debate in philosophy of science, scientific realism. The big question: should we believe that our best scientific theories are actually telling us the truth, or something close to the truth, about the world? Especially about the bits we can't directly see, like electrons, black holes, genes.
Or are these theories just useful tools, useful fictions maybe, that help us predict and control the observable world? That's the opposing view, generally called anti-realism or instrumentalism.
There's that classic example from Arthur Eddington, right? The two tables.
Yes, Eddington's two tables. There's the familiar table of common sense, solid, colored, continuous. And then there's the scientific table, mostly empty space with tiny electric charges whizzing around. Vastly different descriptions. It starkly highlights this gap between appearance and the reality described by science.
And historically, this connects to ideas like primary versus secondary qualities.
Exactly. Philosophers like Locke distinguished primary qualities, properties things supposedly really have, independent of us, like shape, size, motion. Our ideas of these were thought to resemble the qualities themselves, and secondary qualities like color, taste, smell, which were thought to exist only in our minds, produced by the primary qualities interacting with our senses.
But modern science seems to challenge even the primary ones, doesn't it? Like mass isn't absolute in relativity.
Precisely. The scientific picture of reality keeps getting stranger, further removed from our everyday experience.
This also connects back to that deep skeptical problem.
Yeah.
If all we ever directly experience are our own sensations, our own ideas or impressions,
what philosophers sometimes call ideaism,
how do we know there's an external world causing them at all? Could it just be a dream or the matrix, the brain in a vat?
it's a profound skeptical challenge. How do we bridge the gap from our private subjective sensations to knowledge of an objective external reality? It seems we're trapped behind this veil of perception.
And some philosophical movements tried to tackle this head on, like the logical positivists.
Yes, the logical positivists in the early 20th century were radical empiricists. They wanted to ground all meaningful scientific language firmly in direct experience. They talked about protocol statements, basic reports of observation like red patch now. They even tried to argue that statements about physical objects could be translated into statements about actual and possible sensations, a view called phenomenalism. Like, there is a table just means if I were to have certain sensations, I would then have other sensations like touch if I reach out.
But that project ran into serious trouble, didn't it?
It did, especially with theoretical terms in science like electron or gene or even temperature. It proved incredibly difficult, maybe impossible, to define these purely in terms of direct observations without losing their explanatory power.
So if phenomenalism didn't work, how do realists argue for believing in these unobservable entities?
A very common argument is inference to the best explanation, or IBE, sometimes called abduction. The idea is, look, our best scientific theories, the ones that talk about electrons and fields and so on, are incredibly successful. They make amazing predictions, they explain a vast range of phenomena, they lead to new technologies. The best explanation for this incredible success, the realist argues, is that the theories are actually true, or at least approximately true, that these entities they talk about really exist.
It would be a miracle if they weren't true, but worked so well.
Exactly. That's often called the no miracles argument for realism. Why would a theory based on fictions be so predictably successful? The simplest, best explanation is that it's latched onto reality.
Okay, but there's a powerful counter-argument, isn't there? The pessimistic meta-induction.
Yes. Larry Laudon famously pushed this one. He said, look at the history of science. It's littered with theories that were, in their day, incredibly successful empirically. They made good predictions, they explained things. Think of the caloric theory of heat as a fluid, or the ether theory of light waves traveling through an invisible medium, or older theories of generation.
And we now think their central theoretical entities, caloric fluid, the ether, don't exist.
Exactly. According to our current best science, those terms fail to refer. So Laudon argues, by induction on the history of science itself, we should probably expect that our current best theories, despite their success, will also eventually be replaced. And the theoretical entities they postulate, maybe electrons, quarks, who knows, will also be seen as non-existent by future science. So why should we believe in them now?
That's a pretty sobering thought for realism. Does making novel predictions help? Predictions of entirely new phenomena.
Realists often emphasize novel predictive success, like Fresnel's wave theory of light predicting a bright spot at the center of the shadow of a circular object, something totally unexpected based on particle theories. Realists say this kind of success is particularly hard to explain unless the theory is true. It wasn't just accommodating known facts, it genuinely anticipated something new and surprising about the world.
But anti-realists might still say, well, maybe the theory was just empirically adequate in that domain. It doesn't force us to believe in the underlying entities, the waves in the ether, for example.
Right. And this leads some realists to try and refine their position. Maybe we shouldn't be realist about entire theories, but only about those parts that were essentially involved in deriving those novel predictions.
Trying to separate the bits that really did the work from the speculative or incorrect bits, like the ether itself in Fresnel's case.
Exactly. But critics argue that figuring out which parts were essential often looks much easier with hindsight. It can be hard to do prospectively and might seem a bit ad hoc, tailored just to save realism from historical counterexamples.
So if full-blown realism about entities is tricky, are there other options?
One influential idea is structural realism. This view suggests that maybe what we should be realist about is not the entities postulated by theories, the things, but the mathematical structures, the relationships and equations that the theories describe. The idea is that even when theories change radically, like from Fresnel's ether waves to Maxwell's electromagnetic fields to quantum electrodynamics, there's often a continuity in the underlying mathematical structure. That structure, the structural realist argues, is what science is really latching onto in reality.
Okay, that's one way. What about the anti-realist side? Is there a strong modern version?
Yes, Bastien-Fresson's constructive empiricism is probably the most prominent contemporary anti-realist view. Van Frasson says the aim of science isn't truth per se, the aim is empirical adequacy. A theory is empirically adequate if what it says about the observable phenomena, past, present, and future, is true. It needs to save the phenomena.
And what about the unobservable stuff, electrons, fields?
For Van Frasson, we should remain agnostic about those claims. Acceptance of a theory involves believing it's empirically adequate and using it for research and prediction, but it does not require believing its claims about unobservables are literally true. He argues that believing in the unobservable parts is taking an unnecessary epistemic risk. It goes beyond the evidence.
You have that famous saying, right?
Yeah.
About sheep and lambs.
Yeah. It is not an epistemological principle that one might as well hang for a sheep as for a lamb. Meaning, just because you take the risk of believing the theory is empirically adequate, the lamb, doesn't mean you should take the much bigger risk of believing it's true about unobservables as well, the sheep. Especially since, he argues, believing in the unobservables doesn't actually give you any additional empirical predictive power beyond believing it's empirically adequate. So why take the extra metaphysical leap? He calls it inflationary metaphysics.
So where does this leave us as people trying to understand science? When science talks about the Big Bang or subatomic particles, things we can never directly see. Should we think of these as literal descriptions? Or just as incredibly powerful ways of organizing what we can observe?
It really forces you to think about what it means to believe a scientific theory, doesn't it? Is it about truth or about empirical adequacy and usefulness? It's a debate that cuts right to the core of what we think science achieves.
So we've covered a lot of ground. From just the daily impact of science all around us to these really deep philosophical questions about its nature, its methods, the reality it claims to describe, we've seen there's actually a huge amount of debate about what even counts as scientific, how we get knowledge from it, and whether we should take our best theories literally, especially about the unseen parts of the universe.
And grappling with these debates, I think it's really crucial. It fosters critical thinking. It pushes you to question assumptions, even assumptions about science, which we often take as our most reliable source of knowledge. Whether you end up leaning more towards realism or maybe constructive empiricism or some other view, just recognizing these underlying philosophical questions, I think it enriches your whole appreciation of what science is, how it works, and how it changes.
It is definitely a lot to think about, isn't it? If the history of science really does show that even our most cherished, successful theories can be overturned or radically revised, and that our very understanding of reality can shift so dramatically, what does that really imply for the scientific knowledge we rely on so heavily today? We hope this deep dive leaves you, well, curious, maybe with more questions than answers, but with a desire to keep exploring these profound issues at the heart of how we understand our world. Until next time, keep digging deeper.